valency shell electron pair repulsion theory. VSEPR. Valency shell electron pair repulsion theory. So actually, this VSEPR theory was contributed originally by Sidgwick, because we should remember the scientists behind them also, and Powell. Later on, it was further developed by Niho and Gillespie. Gillespie, 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 in 1950. So they found in 1940. Then later they developed as a beautiful concept 1950. So they formed some postulates, take down postulates. The number of valency shell electron pairs, the number of valency shell electron pairs present around the central atom decides the shape of the molecule. And these valency shell electron pair, they can be of two types. One can be bonded electrons, they involve in bonding. They are represented by a bond like this. And non-bonded. Non-bonded means they don't involve in the bonding, but they simply present. So they are represented by a lone pair like this. Lone pair of electrons. So for our convenience, let me put this is Be, this is non-bonding electron, and this is, I mean, bonding electron, this is NBE, non-bonding electrons. Some people they call it lone pair of electrons also. Okay, right. Be and NBE. Second point. The electron pairs of valence shell, they repel one another. So these pairs, electron pairs, repel one another. Because of the electron clouds are negatively charged. So because of negative charge, electron clouds. Usually like charges, they repel each other. So electrons, they repel each other. So electron clouds, there is a repulsion between two groups. Third, these electron pairs arrange themselves. So in order to avoid some fighting, some confusion, some excitation, they try to keep afar. Afar means keep a distance. Okay. So the third point is the electron pairs maintains a minimum repulsion by maximum distance, by keeping maximum distance. Okay, what is that? The electron pairs, they attain the minimum repulsion. How? By keeping maximum distance between them. Next one. So the valency shell is considered to be a sphere in which the electrons are localized. Localized. The electrons are localized on the spherical surface at maximum distance from one another. They try to have a maximum distance with maximum distance among one another. Next one. A multiple bond is treated as if it has got a single electron pair. Multiple bond is treated as if it is a single electron pair. The two or three electron pairs, two electron pairs or three electron pairs are treated as a single super pair. Next. So the multiple bond means what? Single, double bond, triple bond, etc. So when they have two electron pair or three electron pair, they are put together called a single super pair. Shall I move further? Next. If a molecule has several resonating structures, VSP or model is applicable to any one structure one. Let me say a molecule that can be represented by various resonating structures like R1, let me say M1, M2, M3, M4, like that. Okay. So they are all resonance structures. I hope I already indicated the resonance by double-headed arrow. How to represent a resonance? Double-headed arrow. Okay. Yeah. So these are all. So in these cases, you have to consider only one. If a molecule has several resonating structures, the VSPR model is applicable to any one structure. When you target this one, you have to put VSPR only for this. You should not change it. So for only one structure, we have to target. Next, I'll be explaining using the example of these postulates. A lone pair occupies more space. What is this lone pair? What I said, non-bonding electron. So the non, and that is why you would have seen when I draw the ammonia, the structure of ammonia, we used to write like this, NH3 like this. and this is kept alone without any disturbance. And that's why, so it tries to occupy the major space and they are kept alone, right? So lone pair occupies more space, take down, than a bonding pair. So the repulsion between the different lone pairs, I mean different electron pairs, they follow this order. For example, lone pair LP to LP because it needs more space. So the repulsion will also be more here. Do you understand this? Okay. And the lone pair to bonded pair. Then it is a bonded pair to bonded pair repulsion. So it is simply represented LP repulsion is more than that of LPBP, because it needs more. So this is like an elephant. When you want to accommodate two elephants, will your room accommodate? Okay, right. So lone pair, the repulsion will be more. What about this lone pair and BP is less, whereas a BP to BP bonding pair is much less. So among this, which is very, very high? This one. Okay. Now the 8 point. The repulsive force decrease sharply. Repulsive force. I am talking about this as the repulsive force. So this repulsive force decreases sharply as the angle between the electron pairs increases. Angle between electron pairs increases. Okay. So with the increase of angle, there is a decrease in the what? The repulsive force. In fact, the lone pairs of electron are localized on the central atom. Okay, take down. Lone pairs are always localized on central atom. Whereas bond pairs are tagged between two atoms. So consequently, lone pairs of electrons occupy more space compared to the bonded pair. Now let us discuss the various shapes of molecules. Quickly, we can do it so that we can complete this VSPR. Take down molecule type, number of bonding pairs, number of lone pairs, arrangement of electron pairs, then tentative shape, and let us put some examples. So let us consider the AB to E type. AB to E type. Here there are two bonded pairs and one. For example, central atom is A, and you got one pair, lone pair, and two bonded pair. Are you able to understand AB, AB, right? So it will form a bent structure naturally. So, example, you can have no. This you should not include. It has no bond. No? You have to consider only the bonded atoms. So bent, it is angular. That's all. Bent V-shaped structure. So bent structure. Example: sulfur dioxide, ozone, electron pair. So that represents a electron pair. One electron pair is present. Okay, you understand this? Okay, next. I think that is it is getting late. I'll do one thing. I will explain one structure, and based on that, I'll give you a notes. You please go through that graphics. You can easily understand. Okay. So based on this, I'll try to explain so that let us move fast. For example, let me consider water molecule H2O. We expected, listen to me, we expected that is OHH, a linear structure, okay, for water. But this is wrong. Why? Because you've got two lone pairs of electrons for oxygen. So they try to occupy the maximum space, right? So there is a repulsion. This repulsion causes some pushing of bonding electrons down. So it becomes OH like this. Are you able to follow? Now this becomes, they keep afar. Are you able to follow? So they keep the maximum distance. That is why water is a bent structure, a V-shaped structure, whereas a linear is rolled out. So this is explained based on the what? VSEPR theory. Okay, so likewise, you can go through the structure of tetrahedral structure of methane, trigonal pyramidal, etc. So in the next class, I'll be able to explain briefly about various structures formed by this and supported by this VSEPR theory. Okay, right.